We'll study software engineering concepts applied to AI. The concepts to analyze are abstraction, modularity, component interaction. Abstraction help us to manage complexity. In systems design there are two important terms: HLD, high-level design, LLD, low-level design. Abstraction separates high-level system logic from low-level execution details, such as raw matrix math, hardware-specific optimization, model provider APIs, and complex data pipeline state management. AI systems structure abstraction across distinct operational tiers, ensuring that changes at the infrastructure or provider level do not break business logic. The first layer is the application layer. This layer has the responsibility of coordinate high-level workflows, orchestration and take care of UI, UX. In this layer, abstraction decouples specific model choices and back-end infrastructure. The second layer is the model access layer, also known as API layer. This layer must define standardized interfaces for model inference. In this layer, abstraction allows swapping LLM providers. For example, change OpenAI to Anthropic or a self-hosted VLLM, just changing a string config. The third layer is the framework layer. This layer must define neural network topology and how to manage loss calculation and gradients. In this layer, abstraction exposes high-level primitives hiding backpropagation math. The fourth layer is the hardware layer. This layer defines hardware compilation and tensor parallelization. In this layer, abstraction converts high-level operations into hardware-optimized kernels for GPUs, TPUs. The core patterns of abstraction in AI are strategy pattern, vector store, memory abstraction, data ingestion pipelines, and model wrappers and pipelines. Strategy pattern. High-level AI tools use polymorphic wrappers over model APIs. For example, calling model predict abstracts away whether the request routes to a local Hugging Face model via PyTorch or if it routes to a remote API endpoint over HTTP. Memory abstraction. This pattern unifies interfaces and hide the database engine details. For example, you can hide Pinecone, Qdrant and PG vector behind standardized methods like similarity search executed by a vector store. Data ingestion pipelines. Abstracts readers and loaders to convert heterogeneous data sources like PDFs, SQL databases and web APIs into standardized document objects containing page content and metadata before vectorization. Model wrappers. Scikit learns functions like fit and predict, abstract thousands of lines of mathematical optimization, treating linear regression and deep neural networks through identical interfaces. Software modularity divides an AI system into independent, interchangeable modules, each managing a single responsibility. For example, data ingestion, model inference, or storage. Applying modular design to AI mitigates common challenges such as vendor lock-in, data pipeline fragility, and monolithic model coupling. Core architectural modules in AI systems are data ingestion and ingestion pipelines, embedding engine, vector and memory store, model inference, LLM or ML, data ingestion and ingestion pipelines have the responsibility of extract, clean, and chunk raw data, use as input, unstructured or structured raw data, and provide as output clean document or chunk objects. Embedding engine's responsibility is convert text and media into vector representations, uses as input text or image chunks and provides as output numerical embeddings, for example a list of floats. Vector and memory store job is index, store and retrieve embeddings, uses as input queries and vectors and generate as output top K matching documents. Model inference generates predictions or text from prompt or features and produces completion or class probabilities. Orchestration agent has the responsibility of manage execution flow, tools and business rules, generates the final result using as input and user task. Separation of model access from logic. Keep provider-specific code isolated. For example, keep OpenAI, Anthropic and Hugging Face inside isolated connector modules. So, core business logic should interact with a generic interface, making provider shifts a single line configuration change. Decouple data pipelines from training inference. Feature engineering and data transformations should be packaged as standalone libraries or feature stores so both offline training and online serving use identical data transformations. Pluggable evaluation. Treat model evaluation as an independent component that runs against model outputs asynchronously, evaluating metrics like hallucination rates, toxicity, or F1 scores without polluting the inference flow. In AI software architecture, component interaction as a design feature means explicitly structuring how independent AI subsystems, such as retrieval engines, prompt managers, inference routers, tool executors, and memory layers communicate through formal contracts, protocols, and event loops, rather than running AI tasks as continuous, monolithic executions. Modular architectures treat models and their supporting systems as discrete components that exchange structured messages. AI architectures rely on specific patterns to govern how individual components exchange state and control. Pipeline sequential pattern makes the component's output the direct input to component B. This pattern is primarily used in RAG systems, and its key architectural feature is that establish a simple data flow with high predictability and low latency overhead. Orchestrator, hub and spoke pattern establish the communication through a central controller who delegates sub-tasks to specialized models or tools. This patterns is used in complex multi-step assistant routing because its key architectural feature is a centralized policy enforcement, single point of monitoring. Choreography event-driven pattern makes its communication through components that publish and subscribe to state updates asynchronously. This pattern is used in real-time monitoring and multi-agent simulation. As its key architectural feature, we can mention that has high scalability and makes a fully decoupled system of components. The blackboard pattern communicates independent components using a read and write shared state memory space. Is used in autonomous problem solving consensus systems, and its key architectural feature is shared contextual state across heterogeneous models.